Hi, my name is Claudio Gallicchio from the University of Pisa, Italy, and today it is my great pleasure to welcome you to this AAAI 21 tutorial on deep randomized neural networks. The content of this tutorial is mainly taken from a recent book chapter that I have co-authored with my colleague Simone Scardapane from the University of Rome. The chapter is actually entitled Deep Randomized Neural Networks, and you can also find a publicly available preprint version on arXiv. This tutorial is also an accompanying webpage where you can find the link to download the slides, a link to the paper, and other resources. All right, our main focus in this tutorial is to analyze and study randomization in neural networks architectures, and in particular in deep learning. However, randomization is a sort of a big thing, and it can actually enter the design of neural networks in many ways, for instance, in the training algorithms, in the regularization techniques, etc. Here, we focus on the so-called random weights neural networks, in which a great part of the weights in the neural network are left fixed after the initialization, and only a small part, typically those pointing to the output of the connections in the neural networks, are adapted on a training set. Fine. Regarding the outline, we are going to start with a brief introduction to motivate the interest in random weights neural networks, to see why we should care about it. Then we study the case of randomization in feed-forward shallow networks, and this serves as a basis to move forward to the case of deeper random weights feed-forward architectures. After that, we analyze the case of randomization in recurrent dynamical neural networks, and then we see what can be done and what happens when we move to deep recurrent neural networks with random weights. At the end, we also analyze, as a further topic, the case of randomized neural networks for graphs. Okay, this is a quite short tutorial, 1 hour and a half, and of course it can be complete. The intention, however, is to try to sketch the major directions in literature, to see some nice highlights from neural networks literature on the topics related to randomization in neural networks. So my hope is that at the end of this tutorial, I have convinced you to give a chance to randomize neural network algorithms also in your research projects. Fine. Let's start with our first question, our main question. Why should I care about randomization in neural networks? And well, we all know deep learning models achieved a tremendous success over the years. This is certainly extraordinary. Nowadays, deep learning has been very much popularized. Today, compared to a few years ago, it is extremely easy to train and deploy even a large deep neural network that can achieve very high levels of accuracy in a lot of real-world problems. And this is great. However, in practice, when you deploy a deep neural network, accuracy is not only the only, let's say, constraint that you might have. You could also have other constraints, for example, in terms of time and efficiency of your algorithms. And these directly connect to constraints in terms of the number of tunable parameters in the neural architecture. So the point is, do we really need a trainable deep neural network, a fully trainable deep neural network, also when we have all of these constraints? Do we really care even for a point or some decimal points in the accuracy, even if this comes at the cost of a very, very high training time or very, very high computational resources demand? Okay, so there are cases where perhaps we don't want to do that. So we want to find alternatives. And for example, these are some typical examples can come from the area of embedded applications, like 5G applications, for example, or for computing platforms applications, or autonomous driving systems, etc. In this case, the aim is, in general, to embed some sort of intelligence inside the system. Um, and this can be possibly a distributed intelligence across many devices. And this, let's say, system possibly would need to scale to a whole variety of hardware supports, including low powerful devices where, for example, you don't have the GPUs to speed up your training algorithms. So in these cases, you might have an embedded system that does only the inference, which can be easy, but sometimes you also need a system that is also able to adapt, like, for example, adapt to a different speaker, or maybe need to adapt to a different driver of the vehicle, or to a different user that needs to be monitored, etc. So in this context, you need an AI solution that is very, very efficient, especially during the training phase. It might need to adapt in a few seconds or milliseconds during the training. And this training should be performed locally and on the possibly low powerful devices. Okay, so like I said before, we all know that deep learning is great, and there are many interesting results in the literature that show the great potentialities of this, let's say, deep setting in artificial neural networks architectures. I'm not going to dive into this, but let me just do a simple consideration. A popular viewpoint is that deep learning represents a great change, a significant change from end assigning features to learning these features from the data. However, perhaps we can see this change in a better way, like moving towards end assigning architectural biases in the neural networks architectures themselves. This, in combination with the flexibility of automatic differentiation or SGD, etc., can perhaps explain to a large extent the success of deep learning models that we have seen in the last decade. So we can see briefly deep learning, let's say, like a composition of architectural biases plus learning algorithms. And when we deal with randomized deep neural networks, loosely speaking, we remove the training algorithms from this equation. And we, in a sense, we see how far we can go by only relying almost exclusively on the architectural biases. And so in brief, we have a sort of complexity accuracy trade-off, where we start with linear models like linear regression and linear classifiers. These have low complexity. You can train them in a split second, fine, but they also have a very limited accuracy because the linear modeling assumption might not help always. For example, when you want to model a nonlinear phenomenon. Then in the plot, we have things like SVMs or random forests or any other kind of powerful classical machine learning technique. These have a higher complexity, but they are also more accurate. And today, of course, we have deep neural networks that are at the other edge of the spectrum compared to linear models. These are featured by a huge amount of complexity, but they also can have very, very high accuracy. They have state-of-the-art results in a huge number of cognitive-related tasks like video processing, image processing, text, and speech processing. And then we can think of deep randomized neural networks as being here in the plot. The idea is that this kind of algorithms can give an advantageous trade-off between accuracy and complexity. They can have a much higher accuracy than linear algorithms and standard machine learning algorithms because they exploit the architectural bias of deep neural networks. But at the same time, they have much lower complexity compared to deep neural networks, fully trained deep neural networks, because they try to do away as much as possible the backpropagation and the full training of the architecture. And this is the philosophy. This comes from a very well-known quote from Jaime and Dracht, who introduced the random kitchen sinks, one of the basic shallow models in this paradigm of randomization that uses random features to speed up the operations of kernel machines. Actually, their paper from 2007 won the Test of Time Award 10 years later in NIPS 2017. Essentially, in their random kitchen sink paper, the one from 2008, actually they say that randomization is computationally cheaper than optimization. So this can be our philosophy in this tutorial. Actually, in many cases nowadays, in commonly used deep learning algorithms, we tend to use over-parameterized and complex systems. And empirical methods that often achieve the accuracy that we desire, okay, are featured by this over-parameterization. But these algorithms, these models, these learning models are both hard to be trained and costly, okay, and also difficult to understand, analyze, and describe in a clear, rigorous way. Okay. On the other hand, randomized models like random kitchen sinks can be considered both as good baselines, solid baselines, and can also be analyzed mathematically in a very clean way. So overall, I think this is a very important concept, and perhaps this is a concept that has been lost in modern deep neural networks research and practice. Okay, after this introduction, let's dive into the first part of this tutorial and let's try to examine randomization in feed-forward neural networks. Well, actually, randomization in neural networks is here since the very beginning of the field. In fact, perceptron already had some randomization inside its design. And specifically, the architecture of the perceptron contained a first layer, let's say a hidden layer, that took in input the signals from the retina and projected into a feature space using randomized connections. Only the weights from the first layer, from this first layer to the last layer were optimized. And this is why it is generally considered to be a linear model. And also in statistics, randomized projections are actually an extremely powerful tool because they can achieve similar performance, for example, to PCA, but with a much lower complexity. All right, coming to the formulas in the slide. In this case, you have a data matrix X that you want to reduce in terms of dimensionality, and random projection is performed by a matrix R, where the elements are pseudo-randomly generated and allows you to transform the uppercase D dimensional space, where the rows of X live, into a lower dimensional space with a number of dimensions given by lowercase d, using only a simple matrix multiplication. If you do PCA, you have a matrix R, which has some nice special and cool orthonormal characterization. But in random projections, you simply generate randomly this matrix using some constraints, of course, and you can show, for example, using some tools such as the Johnson-Linde-Strauss lemma, that actually, even if it is randomized, it has some nice, pretty powerful characteristics. And in fact, for example, the distances between the points are nearly preserved. This is a very famous first example of how randomization under certain constraints can be very useful in applications to speed up the computations. And in this paper, we can see a recent example of this concept in practice. The example is given by intrinsic dimensionality. Here the question is, let's say loosely speaking, related to measuring the difficulty of a learning problem. And the starting point is that one might think to count, for example, the number of free parameters in a deep neural network that can find a solution to this problem. But actually, how many parameters are really needed? Like we said before today, we know that in many cases, deep neural networks are over-parameterized. So in this case, in this paper, the concept of random projection is used to project the parameter space of the neural network into a smaller and randomly generated subspace and noting the number of dimensions in which the solutions appear. Which is defined as the intrinsic dimension of the problem. In the plot that I have reported here, it is shown the results in the case of MNIST for both fully connected and COMNETs. And interestingly, the results highlight that actually the 90% of the entire accuracy of the full network can be obtained with a much smaller network. where the size is indicated by the red dots in the plots. This also means that the networks in this case are really much compressible. Fine. Let's see now how we can describe the simplest random weights neural networks algorithm. Okay. For example, consider a generic function approximation task, where we denote by x the input vector, and by fx the model that we want to train. We compute this function by linearly combining a number, uppercase H, of randomized functions hi, x. These are linearly combined through the adaptable coefficients beta I. And these hidden functions hi, like I said, are randomized and can, for example, take the form of sigmoid basis expansion with random coefficients wi and b. Good. This elementary kind of model is being proposed in several disguises and popularized in different contexts under different names with slightly different properties. And in particular, like I have reported in the bottom of the slide, the random vector functional link, the random kitchen sinks, the extreme learning machines, the stochastic configuration networks, the no-prop algorithm, etc. Okay, so the essential thing in common is that the inner projection is randomized and the outer projection indeed is learned. And this is graphically depicted in this slide, where we see the very elementary shallow feed-forward architecture. The network as a whole computes a function f, which is a composition of two building blocks, an output function g, computed by a linear model, and the representation function fr, computed by a hidden representation layer. The hidden representation layer is based on fixed connections, randomized connections, and the output function is the only trainable part of the architecture. And the training can be performed easily. Suppose you have a training set with input-output pairs xi, yi. As we have seen, we initialize the input to hidden parameters randomly and collect the corresponding features expansions h of xi, row y, in a matrix capital H. The learning problem then can be cast in several forms, and there are several variants of optimizations that are feasible. However, by far, the most common technique is to use a formulation of L2 regularized least squares, like it is reported in the middle of these slides, where y is the vector of targets and lambda is a free positive hyperparameter. Often, the learning problem is solved in one go, let's say in closed form, by using ridge regression, as indicated in this last formula, where I is the identity matrix of the appropriate shape for summation. Of course, there is a wide range of variants of the basic problems that are possible, like, for example, including the reformulation of the problem in terms of logistic regression, or replacing the squared L2 norm with the L1 norm of beta for regularization. And in fact, this is a model that has a number of properties that are very interesting. First of all, it's a universal approximator because you can just increase the dimensionality of the hidden layer, and you can show that the order of the approximation decreases as the square root of its dimensionality. Another cool thing is that you can have a closed form solution here, because you can end up with the least squares regression, or for instance, you can exploit almost anything that comes from the linear literature. So for example, if you want sparse solutions, you can use the lasso algorithm. Or if you want a more robust model, you can use the Huber-Loss function. Everything that comes from the linear literature can be exploited more or less directly here and straightforwardly. And overall, I think perhaps the most amazing feature is that they are very much faster to be trained than fully trained alternatives. They are also very simple to implement. and also they are amenable to clean mathematical analysis. Now, coming to the cons. Like one hidden layers neural networks, are universal approximators, we know, but maybe you need too many neurons, or otherwise you might not be able to find a good solution. Well, the same happens here too. So in practice, the inner dimensionality can blow up exponentially, and the advantages can vanish. And also another, let's say, relative problem is that these kind of models have a rather interesting and, let's say, complicated history because they came up from the perceptron. So perhaps you can say there is nothing new in proposing models like these. And then also there are many names for basically the same properties and the same ideas and the same concepts, although with little differences, like the extreme learning machines, the random kitchen sinks, random vector functional links, and so on. So sometimes the relations between these different research groups were not really super friendly in this context. I think by now this is a very minor aspect, but in the past years, let's say this has been a non-negligible issue. So I think this is solved now, but be aware of the fact that the history of this kind of algorithms for shallow networks are a bit complicated. Well, in this slide, I summarized the idea of random kitchen sink from a blog post. This is also a quote from Ali Rahimi at NIPS 2017 during the presentation for the Test of Time Award that we have already set. On the left of the slide, also, you can see the code in MATLAB that you need to make the random kitchen sink work. So this is not very different from other alternatives that we have mentioned. And this is just a very precise idea on the simplicity of the implementations in this case. So coming to the quote, basically in this famous talk, Rahimi said that sometimes you are in a good mood and let's say you have the idea, wow, random features are so powerful because they can generate very rapidly a model that solved my problem. Okay, other times you are, let's say, more in a bad mood. You might think, well, this problem was too easy to be solved, that even a randomized algorithm could solve it. Okay, so okay, despite these considerations, all in all, what remains, I think the key point is that regardless of these considerations, randomized algorithms are really an easy trick to try, and they can give you immediately a very strong baseline for a lot of problems. So they are worth to be investigated. Okay, let's now begin our tour in the exploration of randomization in deep neural networks architecture. Okay, to begin, let's consider a generic deep randomized neural network that can be composed, as in the previous case, like the composition of an output function performed by a readout part and a representation function computed by a hidden representation part of the architecture. So we can have more complicated settings, but the most simplest one is the one depicted in the slide, where you have that the representation function, what we call FR, is computed by a stack of multiple layers with random weights, the green part with the ovals in the slide. And this is a quite straightforward extension of the previous model, where we, in practice, in the formulas, we allow the matrix capital H to be generated by more complex architectures with random weights rather than a single fully connected layer. Okay, and irrespective of the accuracy of these kind of models, an analysis of its theoretical properties is interesting, I think, because it corresponds to investigating the behavior of a deep neural network in a small subspace in the neighborhood of its random initialization. So what happens at the beginning of training, if you want. So you can use deep neural networks with randomized layers as an explorative tool from the theoretical point of view. And some of the most interesting theoretical works today are based on considering a random neural network, seeing it like a random variable, and see what happens when you propagate the computation towards the higher layers. For example, in this ICML paper, it is shown you can get generalization bounds from this random neural network setup. And in fact, there is a vast literature nowadays showing insightful connections and interesting connections of this problem with the study of kernel machines and Gaussian processes. You can have a look at our book chapter for more insights in this regard. And another interesting result in this sense is given, for example, in this paper that generalizes most of the previous results for a vast class of representation functions, FR. Whose structure can be described by a directed acyclic graph like reported in the picture in this slide, when we associate to each node a bounded activation function, and this comprises most commonly used feed-forward and sequential neural networks. What they show in this paper is that the skeleton of this function, so the topological structure without any knowledge on the weights, is associated univocally to a kernel function K. And the representations generated by a single realization of the skeleton that you can obtain by sampling the weights from a Gaussian distribution with appropriate variance are in general able to approximate the kernel K itself. Also, a complementary class of results is based on the novel idea of the neural tangent kernel. You can have a look at the book chapter to get a deeper insight on this and on the relations with the literature. And another interesting class of results is obtained in this paper, reported in the slide, and in later works. The idea is to explore the effect of the randomly initialized representation functions on the metric space in which the data lives, the data resides. So if we assume that the points in input data that correspond to separate classes have large angles compared to the points in the same class, then it is possible to show that our representation function FR, the one that is randomized, computes an embedding of the data in which the latter angles are shrunk more than the angles corresponding to points in different classes. And I think this is better represented here, illustrated in this figure from the paper. In essence, the angles between different classes tend to become larger, and the angles inside the same class tend to become smaller. So in practice, the authors prove that deep neural networks with random Gaussian weights perform a distance-preserving embedding of the data with a special treatment for points in class and out of class. So with the separation among the classes increasing, the embedded obtained by a deep network makes the data easier to be classified by, for example, prioritizing their angles in the classification. Well, and another interesting strand of works tries to combine the advantage of randomization with some partial form of training, in this case by using the concept of staked out encoders, similar to the prior works on deep learning. So here, I just limit myself to recall you that an autoencoder is a neural network with one or more hidden layers that is trained to map an input X or a corrupted version of it to X itself, learning a suitable intermediate representation internally in the network. So a general recipe to combine autoencoders with random vector function link-like neural networks is described in this paper from IJCNN 2016. So it's based on 4 very simple steps. Number 1, you initialize a random mapping H of X, similarly to what we have seen in the shallow models in the previous part of this tutorial. Number 2, we train the readout to map H of X to the original input X. And so in doing so, we obtain a set of weights beta, okay? For example, using least squares solutions. Step 3, we use this beta transpose as the first weight matrix of a separate deep randomized neural network. And step 4, we continue the construction of our network, repeating points from 1 to 3 based on the embedding generated at point 3 of this simple algorithm. So you can see it's very, very simple. So the idea is very simple, but it can be shown that actually in several contexts, it is possible to get some powerful accuracy just in a few seconds. So like demonstrated in the paper. So if you have a very large data set, then in few seconds, again, you can have some very powerful baselines. And interestingly, although until now we have focused a lot on densely connected neural networks to describe our ideas, actually there are a number of works that show that a similar good performance of randomization-based neural networks can be achieved also in the context of deep convolutional architectures. For example, this is nice work, I think, in which it is shown that even by fixing almost all the layers of a deep convolutional neural network, um, freezing even the majority of the parameters often results in a performance that is similar to the one that you can achieve by learning all of the weights. And in this paper, there are actually a huge number of experiments. You can have a check with several types of convolutional networks in different conditions. And the fact of fixing the weights is studied and analyzed in several perspectives, like, for example, randomizing the weights or setting them to 0, randomizing entire layers or randomizing only some filters in the layers, randomizing the convolutional layers in the architecture or randomizing only the output layer in the architectures and training the layers below that. So in this table, you can see just one example of the results that are reported in the paper, an interesting one, I think. So we can see in practice in the third row in the table that with 70% of the parameters trained, you only lose something like 2% in the top one accuracy. And if you reduce even more to 40%, then you lose another 3% of the top one accuracy. So you only lose that. So in practice, you can see that it seems like a convenient setup for your network. So apart from these computational savings, this finding is also interesting as it allowed to describe a good portion of the neural network only with the knowledge of the specific pseudo-random number generation generator that has been used like the initial seed. So you can, for example, describe completely some parts of the network by just one number instead of a lot of numbers. So another nice aspect that is once more highlighted in this paper is the common fact that in deep learning, we are currently using many times, many occasions, over parameterization of the models with respect to the performance that you can actually achieve. And this randomization approach is even working well in practice in the case of transformer networks. So what they do in this paper, they actually use this simple organization. They have some weights that are kept fixed after initialization, and some others are trained. Okay, so like exactly like what we have described so far. So especially here, there is an alternation of trainable and fixed layers. So they call this reservoir transformers, and the name comes from the reservoir computing, which I will introduce in the next part of the tutorial. So you can understand this like randomized transformers. Well, actually, what they do, like I said, they have an alternation between trainable and fixed layers. And for the fixed layers, they still backpropagate through them to compute the gradients for the early layers, but they never update their parameters. So they are freezed in a sense in this way. So in practice, this is a very simple setting, but it's a powerful one. And essentially in the paper, it is shown that by keeping some of the layers freezed in the way that I have described to their initial conditions, so using them like random features, so that's why reservoirs, you can both save substantial computational time and still achieve similar performance to the fully trainable networks. And there is another recent work that has been accepted at ICLR 2021, so will be presented. soon, and this introduces the concept of a performer as an efficient way of implementing the transformer network. So in practice, the work here is based on the observation that creating attention tensors is not feasible for long temporal sequences, for example. And the aim that the authors have here is to improve space and time complexity of transformers architectures using the random features idea. So what they do is they show that actually you can decompose the attention matrix A in the figure on the left part into the product of two matrices Q and K, where K is a kernel matrix, and you can achieve this using randomized features. And then using associativity, the products can be performed in a different order, like indicated in the right-hand side of the figure. And this allows, in turn, to avoid the quadratic cost with respect to the sequence length. Okay, so you can have a look at the paper, but the idea is that elaborating on this approach, you can show that now the computations with these performers become more feasible also for long temporal sequences, and larger batch training samples can be used with lower computational time required for every gradient step. Okay, this said, let's try to complete our overview of the possible kinds of approaches that we can have. And an interesting consideration that we can do is that fully trained, also called strongly trained, and randomization-based neural networks, also called weakly trained neural networks, actually, well, they are two extremes of a possible continuum of training models or of neural network models that have a diverse sets of trade-offs between accuracy, speeds of training, speeds of inference, etc. So there is a continuum, a possible continuum of models where we have seen just, let's say, extremes. An example of models in the middle of this range, in the middle of this continuum, we can describe the case of semi-random architectures as proposed in this AAAI paper from a few years ago. So essentially, what we see here is that the hidden feature expansion of our random vector function link based model, so our randomized neural network model, is substituted by the feature transformation that is indicated in the formula here in the middle of the slide, where a part of it is randomized and another part is trainable. And you see there is a function sigma s, and this function sigma s in the randomized part denotes the activation function that depends on a hyperparameter s. And for example, you can have linear semi-random features for s equal to 1. You can have quadratic semi-random features for s equal to 2. And one interesting thing is that although perhaps it is a bit counterintuitive, the model shows a lot of nice properties. The learnable part, in fact, ensures you to achieve good performance in applications, in practice, while the randomized part enables you to study the theoretical properties, like, for example, to prove the bounds, etc. So in applications, you achieve good results, like is reported in the paper, although still with relatively small data sets demonstrations currently. But perhaps even more important than the theoretical and the practical capabilities, this model in this paper is, I think, important because it shows the powerful of a smart combination of the two words, fully trainable deep learning and randomized models, so semi-randomized models. Well, these kind of things, I believe, is still heavily underexplored in the literature, and the moment can be a good idea for future directions and future investigations. Well, and understanding the performance of deep randomized networks in practice goes in the direction of understanding how much the amazing results of deep networks in several domains are due to their architectures, so the architectural biases, like we have said in one of the first slides of this tutorial, and how much can be attributed to the specific training algorithm for adapting the weight. So this is like a fil rouge for our exploration. One key contribution in this direction is given by this very nice and famous paper on deep image prior. which perhaps has been the first paper to show that a randomly initialized convolutional neural network contains enough information, enough structural information to act as an efficient prior in many image processing problems. So in practice, here a CNN with random weights is used to model the prior in the image synthesization or generation, while the process converges towards the solution in the image space. And so this, of course, enables to save considerable amount of computation, because in practice you don't have to learn it. And this very simple procedure that is described in the paper enables to solve surprisingly well many image processing tasks without even training the priors. And examples are provided in this very nice GitHub webpage, like artifact removals from the images in painting, super resolution, denoising, etc. And deep randomization can also be used not only during the forward pass, like at some step of the computation from the input to the output, but also, for example, in the backward pass during backpropagation of the gradients. And this is another very famous and interesting paper called Direct Feedback Alignment from NIPS 2016. So this is an example in this sense. So it shows that when you backpropagate, also in that case, you can resort to the idea of using randomized matrices to speed up the computations. So what we see in this figure from the paper, on the left, we see the standard backpropagation. So you here in this case you use the transpose of the weight matrices for backpropagation, the transpose of the weight matrices that you have used in the forward pass to propagate the gradients. Okay, so in practice, what you can do, you can actually avoid using the transpose of the weight matrices, and you can replace them with random matrices between the layers. Okay, so this is shown in the other columns of the image. In feedback alignment, in practice, you are replacing the W2 transpose and W3 transpose with two random matrices, B1 and B2. And in the third column, you have the direct feedback alignment idea, and this, let's say, randomization idea is pushed even further. And it is shown that actually it is sufficient to directly propagate the error information from the last layer, modulated by these randomized matrices, to the hidden layers directly during the gradient computation step. And in the last column, another variant is proposed, the so-called indirect feedback alignment idea, where in practice you do this trick just for one of the lower layers in the architecture, not even all of them. So in practice, the inference time doesn't change a lot, actually, but training can get way, way faster. And finally, there are some interesting connections also with other topics, like that of pruning, and search in neural architectures. We start along this direction in this slide by showing the lottery ticket hypothesis, best paper award from iClear 2018. According to this lottery ticket hypothesis, in randomly initialized forward deep neural networks, you can find actually some special subnetworks. They are very special. They are called winning tickets. These special winning tickets are smaller, even substantially smaller than the original neural network, the original over-parameterized deep feed-forward network. And you can find them after, by pruning after training. So when trained in isolation after the pruning, okay, these very small architectures, these winning tickets compare very well to the full, much larger neural networks in terms of accuracy in comparable number of iterations, like shown in this image in the slide from the paper. So these winning tickets originate from, let's say, lucky random initialization. And then in a following paper, this connection with deep randomized neural networks become even more clear. So this paper is very interesting and tries to answer a similar question. Let's say, what's it then? What can be found in a randomly weighted neural network? So even without retraining of the pruned smaller network. So the conjecture here changes a little bit from that one of the lottery ticket hypothesis. And that the conjecture here is that within a sufficiently over-parameterized neural network with random weights, there exists a subnetwork, like indicated in the picture, still with random weights, so even without training at all, that can achieve a good performance, even comparable and competitive, sometimes superior, to those achievable by a similar architecture with a comparable number of tunable parameters. So the authors, for example, in this case, not just succeed in finding experimental support to this claim. So this hypothesis that they propose actually seems to be true in practice, but they also propose a simple algorithm to discover such smaller, good performing networks. For example, an interesting thing is that they found that hidden in a randomly weighted wide ResNet 50, what they find is a subnetwork with random weights that is smaller than a ResNet 34, but matches the performance of a fully trainable ResNet 34 on ImageNet. And I think this is really a cool result. And another related problem is that of finding an optimal architecture for a specific task. And this problem is also called neural architecture search. One interesting paper in this field is the one on weight-agnostic neural networks that is indicated here from NeurIPS 2011. In particular, this one is inspired by precocious behaviors observed in nature. And what the authors do is they develop neural networks that can perform naturally, intrinsically, certain tasks, even without learning at all, even with all the parameters fixed. One crucial aspect is that to speed up the search, they use a single weight parameter shared across all the connections. And this enables to evaluate the networks on a wide range of possibilities to explore a lot of configurations in the same time. So instead of optimizing the weights of a fixed network, what is done is it is explored and found an architecture that performs well on a wide number of weights. Okay, so in practice, the algorithm is very simple, has a few steps. Step number one, you create an initial population. Step number two, the population is evaluated over multiple configurations with different choices of the shared weights. Step three, the networks are ranked according to their performance and complexity. And step four, the new population is created. So this process repeats again and again from step two to step four until you find the network that you are satisfied with. So what they do in the paper is they show that they can achieve intriguing performances, so even without explicit training at all. And this simple idea can actually behave well in a number of tasks like image processing and control. Intriguingly too, there is an accompanying website, a nice website, this weightagnostic.github.io, where it is possible to see cool demonstrations, live demonstrations of this approach. So one of the crucial ideas in this paper is to use fixed weights and to use the power of the architectures almost alone. This same idea is actually exploited in many other cases, also when the network computes a dynamical system. And this links directly to the next part of this tutorial. Well, and namely, this is the aspect of randomization in recurrent neural networks. All right, we all know that dynamics in neural networks computation is so important. It is so important because dynamics enable us to treat data where the different elements are in sequential relation. And most of the times, this is a temporal relation, although it can be generalized, for example, to more complex forms of structures like graphs, and we will see example of these. Well, in general, dynamics and feedback loops in neural networks architectures enable us to treat many forms of structured data in general, emerging, for instance, in many interesting applications like IoT applications, human monitoring applications, speech, language processing, autonomous driving application, etc. But also, and very importantly, I think, recurrent neural networks are motivated by the biological brain themselves. And depicted in this slide, you can see the famous hierarchy of the visual areas in the monkey brain from a very popular paper by Feleman and Van Essen. So the visual information from the retinal ganglion in the bottom part of the slide projects to the thalamus, then to the primary visual cortex, and through many, many other components until the information reaches the hippocampus on top of the figure. Now, nearly all of the connections that you see here are bidirectional, and there are a lot of loops. So this motivates the presence of feedback loops inside our artificial neural networks. And another example is given by a strand of works in the field of computational neuroscience, initiated in 1995 when Domini proposed a model of the cortico-striatal system for sensorimotor sequence learning. So the goal of this analysis was related to the neuroanatomical observations in the cortico-striatothalamo-cortical loops that have major roles in a lot of aspects of neurocomputation, like the oculomotor system. So the observation were that a major property of the brain architecture in primates is the presence of massively unstructured projections from the cortex to the striatum. These ones. So these are part of a set of closed loops where the signal goes from the neocortex to the striatum, to the pallidum, to the thalamus, and back to the cortex again. And another important architectural property is the huge number of local connectivity in cortico-cortical connections. So this can be modeled like recurrent connections that provide dynamical systems properties to the computation. So these observations led to this model depicted in the left of the slide, whose main features are the presence of fixed, untrained, recurrent connections in the prefrontal cortex network, PFC, and modifiable connections between the PFC neurons and the neurons in the striatum, indicated by CD, caudate nucleus, in the figure. So these components in the last part form an associative memory that links the dynamical states in the PFC to the desired output responses in this area. So again, it's the same paradigm that you've seen until now, where you have a representation function, in this case randomized recurrent function that is fixed, and an output function that is trainable. And in a sense, this model represented the success of computational neuroscience, where a mathematical model originated from neuroanatomical observation succeeded in explaining with success, let's say, the results of cognitive experiments. And also, interestingly, for the purposes of this tutorial, this is the very first example of a recurrent neural network with fixed, untrained feedback connections. It's very old. It dates back to 1995, and it is actually the beginning of something that has been popularized several years later under the name of reservoir computing. Okay, to frame a bit our discussion, let's say that now we're dealing with recurrent neural networks. Architecturally, the major difference in recurrent neural networks with respect to the feed-forward neural networks that we have analyzed so far is the presence of feedback loops among the hidden layers neurons, okay, in the recurrent units. So this is highlighted in red in the figure in the slide, and this is a crucial modification that makes it possible to elaborate each new input, xt, in the context of its predecessors. So the presence of these feedback loops gives a memory to the operation of the system. And roughly speaking, apart from this architectural change, the basic description of the model doesn't change a lot. So we have, again, a hidden layer that here is made up of recurrent units instead of feed-forward ones. And these implement a representation function fr. The outcome of this representation function is propagated to a readout layer of linear units, typically, that calculate the output function g. So again, the overall operation can be described like before as a composition of an output function on top of an internal representation function. So g composed to fr. And training this kind of recurrent neural network architectures implies gradient propagations across several steps. So the basic operation that we need to do here is unfolding the same architecture that we've seen in the previous slide over the temporal structure of the input time series, as it is denoted in these blocks in the slide, where we have the same, let's say, vertical architecture that is replicated at each time step of the computation. So you see in red the input, in green the hidden representation, in blue the output. And there on top, I just put loss information, which can be injected in the backward process of backward gradient propagation. So it's not surprising then that we can see this, these training algorithms for recurrent neural networks needs to face similar difficulties to those that you can have when training deep neural networks, because when you unfold the architecture over time, you get a deep neural network. And the major consequence of this is that learning is computationally intensive and requires long times. So the natural question that we have, and that motivated at least partially our studies during all the tutorial, is can we find alternatives to this computationally intensive approach? And well, an appealing alternative is actually out there, and it is called reservoir computing. This approach focuses on a major distinctive characterization. Let's say we decouple the treatment of the hidden recurrent layer from that of the output layer. And instead of, roughly speaking, blindly trained by backpropagation the recurrent dynamics of the system, we try to focus on them under the lens of dynamical system theory. So this said, we have a recurrent neural network architecture as before, where the dynamical part is called now the reservoir, and this is tapped by a typically linear readout layer. So like before, the readout is the only trained part of the architecture, exactly like described for the feed-forward models in the first part of the tutorial. Instead, the parameters of the reservoir are left fixed after a randomization-based initialization. And going a little bit more into the details, the reservoir can be seen like a discrete time, nonlinear, and input-driven dynamical system that is ruled by this iterated map function indicated in the formula, and that evolves a state of the system indicated here by ht as a function of the input at the current time step t, let's say that is xt, and of the state at the previous time step ht minus 1. The influence of the new input is modulated by an input weight matrix indicated by W here in the formula, and the influence of the previous state is modulated by a recurrent weight matrix WR. So the cool thing is that we can take the elements of these two matrices randomized. And the crucial thing is that we can do this as long as the implemented dynamical system satisfies a global asymptotic stability property, which in this context and in practice is a fading memory property that is called the echo state property. All right, if this echo state property is in place, then the reservoir dynamics will asymptotically depend only on the input time series, and the initial conditions progressively will fade out in the representation. So in a sense, the activations of the hidden units over time become an echo of the dynamical input features. That's the motivation of the name echo state property. So the state becomes an echo of the input. And although theoretically the story is much longer than this, and I refer, of course, to the references in the book chapter for more information, in practice, the all complicated process of training the recurrent layer of the network is replaced here by a very simple algebraic process of rescaling the eigenvalues, and in particular, the spectral radius of the randomly initialized recurrent weight matrix, rescaled to a value that is smaller than 1. So we denote this by this row of WR smaller than 1. And after that, you're done. So you run your stable reservoir on the input time series, you collect the hidden units activation inside a weight matrix H, like before, and retrain the readout by using pseudo-inversion or bridge regression. As easy as this. Well, this fundamental reservoir concept has been instantiated and independently, let's say, rediscovered in many forms in the literature. For example, a popular model is the Acoustic Network, introduced by Herbert Jager and his collaborators. In this case, the reservoir neurons are standard hyperbolic tangent neurons that operate in discrete time. We use this like the major reference in the tutorial. Another popular approach is the liquid state machine that has been introduced by Maas and collaborators. In this case, the reservoir is called a liquid, and it is a layer of spiking neurons. And another approach that is perhaps a little less popular, but still in the same framework, is the fractal prediction machine by Peter Tigno. This originates from the study of contractive iterated function systems. Okay, fine. You might wonder on which tasks these kind of neural networks are commonly benchmarked, and mostly for their nature, it is this. So acoustic networks and reservoir computing had a lot of success in the prediction of chaotic time series. Here you can see the attractor of a famous biologically motivated dynamical system, that is the Mackey glass system, whose equation is in the bottom right part of the slide. So modulating and modeling the attractors of chaotic time series might sound a bit abstract as an application, though. However, in my experience, I can tell that I have found this type of approach very effective also to solve real-world problems that are very, very practical. Yeah, for example, it is shown one of the applications in the field of ambient assisted living. So in this case, we have a human that lives in a highly sensorized environment, possibly elderly person that needs assistance. So what you have from the perspective of machine learning, you have a distributed intelligence over what we call those times robotic ecology. So in this case, we used reservoir computing-based algorithms for tasks like human activity recognition, human localization, robot localization, etc. So the very cool thing, I think, is that the neural networks could be run and even trained, this is crucial, on super tiny devices like Telos B sensors. On board, you had the sensor and the neural networks to do the computation and also the training. So these Telos B sensors had severe time and memory constraints. Just to give you an idea, 8 kilobyte of memory in total. All right, and regarding applications, as a guide to design and develop acoustic networks applications in practice, I think this paper, A Practical Guide to Applying Echo State Networks by Mantas Lukasevicius, is a great starting point, and so I definitely suggest it to you. Okay, of course, there are so many things and many concepts from the reservoir computing literature that would be worth to be illustrated and described. Of course, we are running out of time, so I can't mention all of them or even get into details, dive into details, but at least I would like to highlight some of the aspects and of the concepts that are important, I think, in reservoir computing. Okay, one of these aspects is the edge of chaos, or edge of stability, or edge of criticality. Well, in practice, and very roughly stated, a dynamical system like a reservoir layer, that is a dynamical system, can be in a number of dynamical regimes, from stable regimes to unstable and chaotic regimes, where tiny little perturbations in the input or in the state grow up exponentially over time. So this is bad. And the edge of chaos is the transition between stable reservoir dynamics, in this case, and unstable reservoir dynamics. And there is plenty of literature in the sense. You can find more in the book chapter. Yeah, just show something from a nice theoretical, both theoretical and practical paper, in which, for instance, it is shown that short-term memorization capabilities of the reservoir have a peak in correspondence of the edge of chaos. So here, highlighted by the red dotted line in the slide, I indicated this edge of chaos transition. In this case, in the paper, to identify the regime that is, it is used to compute the maximum local Lyapunov exponent. So very roughly stated again, values below 0 on the left of the red line denote stable dynamics. Values above 0 on the right part of the red line denote unstable dynamics. And you can see that this memory capacity MC score that you see on the y-axis peaks in correspondence of this transition between stable and unstable dynamics. And another important concept is perhaps that what defines reservoir computing is this separation between the dynamical hidden layer and the training of the readout. So actually, the dynamics in the reservoir can be tuned if you want, and adapted to the peculiarities of your training data. There's a strand of works that tries to achieve this goal, mostly in an unsupervised fashion. So yeah, biologically inspired approaches are most of the times used. And here I just highlight one of those that I think is important, the intrinsic plasticity algorithm, that is based on a neurobiological phenomena that is called homeostatic plasticity. This kind of plasticity is different from the synaptic plasticity, and it is a plasticity of the intrinsic electrical properties of the neurons. So it's not a plasticity between two neurons. And here the idea is to tune the gain and the biases of the activation function of the reservoir neurons, these A and B in the first line in the slide, to tune the probability density of the reservoir neurons activation to a maximum entropy distribution. And this basic idea translates into a local, unsupervised, very simple, and biologically inspired learning of the hidden recurrent dynamics that tunes just those two numbers, A and B. And the rules are given in the second and the third line in the slides, and are derived essentially by minimizing the KL divergence with respect to a Gaussian distribution in this case. Well, another strand of works in reservoir computing is motivated by the idea, let's say, to optimally shape the connections among the reservoir neurons. So instead of having a random generated reservoir, we want to find an optimal, improved, let's say, reservoir. And one nice observation is that reservoirs with orthogonal recurrent weight matrices have actually nice properties, like longer short-term memory abilities. So manipulating, shaping the way in which reservoir neurons are connected is a simple way to enforce this kind of constraints in the neural network. And in particular, a simple approach is to have a recurrent weight matrix that has a structure given by a permutation matrix. Moreover, a very simple, extremely simple case is given by a reservoir topology where all the neurons in the reservoir are organized to form a ring, a cycle. And the simple cycle reservoirs or ring or even multi-ring in some cases have been popularized by a paper called indicated in this slide. So you can find depicted in the image. And furthermore, another important thing is that you can actually use the same weight for all the connections in the reservoir. So the reservoir, as you can see, is organized such that the units form a ring, form a cycle, and all the connections in the recurrent part share the same weight. Okay, so the reservoir is no longer randomized, but it is still fixed, so untrained after the initialization. And this structure, let's say, gives this constraint organization gives a couple of advantages, at least. So first advantage, you can achieve performance that is in the top range of reservoir computing performance in many tasks with a simple architecture. And second, instead of exploring a lot of possibilities with different values of the recurrent weights in the network, you just vary one value. Okay, so clearly in this way you can more effectively explore the reservoir hyperparameter space, the reservoir configurations to find a good one for your task. And these kind of permutation-based reservoirs have been studied also from theoretical perspectives. For instance, in this work by Tigno, published recently on JMLR. In practice here, there is a parallel between the operation performed at the reservoir computing system and a temporal kernel. In the paper, it is shown how actually it is possible to study the temporal kernel and its fading memory properties using the eigendecomposition of an associated metric tensor. The eigenvalues of these metric tensors can be, in practice, viewed, the eigenvectors can be viewed as representative time series motifs, and these are represented in the left part of the slide. The corresponding eigenvalues can be considered like weights and are represented in the right part of the slide. So here it is depicted the case of random reservoirs that leads to this sort of shallow temporal structure with a few motifs, a few components. While here, you see what you get when you move to a permutation reservoir. In this case, you have a much deeper and longer and more interesting, let's say, non-trivial, non-shallow temporal structure. So it's cool that the only thing that you change in practice is the way in which you connect the neurons in the reservoir, and that's it. So you get richer dynamics. And this one is another paper, recent paper, that exploits the parallel between recurrent kernels and reservoir computing. It has been presented a few weeks ago in the last NeurIPS conference. In practice, what they show is that the convergence rate of reservoir computing, they show, sorry, the convergence rate of reservoir computing with infinite width to the recurrent kernel. And this, in practice, is demonstrated to enable achieving very high performance on complicated and very high dimensional time series modeling tasks like the one studied in the paper. Well, a few more concepts to conclude a brief overview of reservoir computing. One is related to the approximation capabilities. Here, in this case, we ask ourselves how powerful are reservoir computing systems. So how powerful is a recurrent neural network without learning of the recurrent connections in practice? So there is a whole strand of works also in this case. This is very interesting. And the main actors of these strands of works are Grigorieva, Gonon, and Ortega. That show in a number of papers interesting results in this context. Perhaps the most relevant one is that acoustic networks are universal in the sense that they can approximate any fed-in memory filter. So this is not really surprising, but intriguingly, this result also not only for the basic case, vanilla acoustic networks with non-linear recurrent component and the linear output part, but also for other versions like trigonometric state-affine reservoirs with linear readout, and also even for linear reservoirs, and I think this is very important, provided that the readout is nonlinear, like for example, a multi-layer perceptron. So this is also a nice strand of works that needs to be considered. And then another nice thing is that reservoir computing is not just a research area, it's also a community of people. And very importantly, I think this community of people has a variety of competencies in it. And for example, an important part of this community is the nonlinear physicist. So long story short, in practice, you can implement reservoir computing in neuromorphic hardware very effectively. There is a plenty of ways in which this can be done, and I refer you to this very nice and good survey of the topic by Tanaka and others that has been published recently on the Neural Networks Journal. So essentially, like you see in the figure on the left, the dynamical reservoir can be replaced by a physical system that has some controllable dynamics and rich dynamics. And for example, like on the right part of the slide, photonics can be used in several ways. For example, implementing the idea of the ring cycle reservoirs presented previously by using time multiplexing. Okay, let's move now to the last part of the content of this tutorial when we try to go deeper in reservoir computing and see what does it mean and what we can achieve. Fine, we start by observing actually that recurrent neural networks architectures are actually shallow. While we have seen that unfolding over time this architecture, you get a deep network. In fact, when you look at the individual transitions and functions implemented, they're actually shallow. So the input to hidden transformation is shallow. The transition from the state in the previous time step to the current state is shallow again. And also the transition from the state to the readout is shallow. So one can, in principle, make deep all of these transitions. And you can find a nice discussion on the various possibilities in this paper indicated on the top of the slide by Pascano and others. In practice, what you can do is you can make deep the input transition, or you can make deep the output transition in the red here. Or, and this is the focus of the next slides, you can make deep the state-to-state transition, having a deep reservoir. Okay, so in this case, we talk about deep acoustic networks and deep reservoir computing. This is a kind of models that we have introduced in literature a few years ago. Deep acoustic networks are reservoir computing models And again, the reoperation can be described by the composition of a dynamical reservoir and a feed-forward trainable readout. The crucial difference with respect to standard shallow reservoir computing is that now the dynamical part is given by a composition, a stacked composition of multiple reservoirs. So in practice, the reservoir is deep. As you can see in the figure, the deep reservoir contains L recurrent layers that are fixed, and the architecture is completed by a readout that is trainable as before. So as the point is that we will actually achieve qualitatively diverse dynamics in the different reservoir layers, sending the activations of all of them to the readout, like it is depicted in the slide, allows the learner to actually be able to give the right weight to each one of the filters. So use this when you want to deal with multiple timescales. However, it could also be useful to project only the activation of the last of these filters to the readout, like in more common deep neural network settings. So use this when you want to explore directly the enrichment of the state dynamics in higher layers and you don't actually need multiple timescale processing. And from a mathematical perspective, it is cool to see that the deep acoustic network is actually a nested set of input-driven dynamical systems, where in practice, we have the external time series xt that drives the dynamics of the first layer h1t. This in turn drives the dynamics of the second layer h2t, and etc., until we reach the L-1th dynamics that drive the dynamics of the last layer, L. And one of the interesting things is that the structure that we have given to the recurrent architecture, let's say, is reflected both in the developed temporal representations. So you can achieve multiple timescales, multiple frequencies representations. And second, also in the mathematical entities that are involved in the analysis, like, for example, in the Jacobians. Coming to the multiple timescales aspect, this is one of the first experiments that we did some years ago in the first paper on the topic. This is a very simple empirical analysis. We drive the same deep reservoir system using two time series, a reference time series and the second time series with a perturbation, just one single typo in the sequence. Then what we do is we record the Euclidean distance between the states in the corresponding layers of the architecture as a function of time. And in the plot, you can see the results. The blue lines here indicate the layers, the results for the layers of the deep network. And we also compare this with what is achieved by a shallow one-layer shallow acoustic network in red. Okay, so interestingly, we see that the effect of the typo in the input actually is lasting longer in the higher layers than in the lower layers. And this effect is cool because it is intrinsic. No learning is taking place here. All the layers are initialized to be asymptotically stable, and that's it. So the structure of the deep recurrent neural network is the only responsible for this effect. These multiple time scales ordered along the hierarchy of the layers are intrinsic. So this is, I think, the most important observation that we can draw here. And originally, we were inspired by this paper in NeurIPS. This paper showed that you can actually have multiple time scales in deep recurrent neural networks if you do ad hoc layer-wise training. But actually, as I showed you in the previous slide, and as we showed in the paper, you can have a check, the effect was actually not due to the learning, but largely and mainly to the architecture. Okay, going ahead with this concept of multiple temporal representations, one can also wonder when to stop the stacking process in the construction of a deep acoustic network. So in this paper, published on Neural Networks Journal some years ago, we started from the previous observations and from the fact that each reservoir layer can be seen like operating like a filter that removes progressively a part of the frequency content in the driving input signal that is propagated across the layers. So in this case, everything is done in an unsupervised manner. So we can try to answer this important question in deep learning. Okay, so how many layers should I use to solve a problem? Well, in practice, the answer is continue stacking until this filtering effect becomes negligible. So you can actually start from your first layer, your first reservoir layer, and you can do a frequency analysis of the reservoir in that layer. So fast Fourier transform of the signal in the layer. So this is plot A, the top left of the figure. Then we can add another layer and repeat the fast Fourier transform only for that layer. We compute the center of mass of the frequency content, and we see if there is actually a shift. And we see, for example, in the B plot, subplot, that there is a shift. This shift is highlighted in the red bar. So this is substantial. Then we continue adding progressively more layers. So we continue, for example, in the second row here, the same operation until we reach a layer, let's say in the bottom right, where this shift is absolutely negligible. So there we can stop. And interestingly, this stop comes at a point after which it would be, let's say, pointless to continue, because in a sense, we would just chase an asymptote. No qualitative difference after that. And the interesting aspect is that this is a good point where to stop, also because, also as it is testified by the fact that the performance is way better than the other literature. The performance that we achieve by stopping at that point is very good compared to alternatives on the same task that you could find by extensive model selection. Okay, we spoke about short-term memory in a previous slide. Well, in practice, another nice finding was that just stacking successive layers of fixed recurrent neurons, so deep acoustic networks, deep reservoirs, as an inherent effect of increasing this quantity, this memory capacity. Here in this plot, you can see the value of the memory capacity score, where the higher, the better, computed for individual layers of the deep acoustic networks. So this is plotted on the y-axis against the value of the spectral radius, the crucial hyperparameter of the recurrent weight matrix on the x-axis. And what you can see, it's apparent that making the network deep is advantageous. And in fact, the memory capacity is almost doubled here from layer 1 to layer 10. So you could actually, in principle, continue up to the theoretical limit of the memory capacity. Now we know that layering improves some measures of richness of network dynamics intrinsically. Like we've seen the memory capacity, it gives also intrinsically multiple time scales and multiple frequency representations. And importantly, these are intrinsic features, like I said. So even in the absence or prior to training of the recurrent connections. And this means if you wanted just stacking the same number of recurrent units, organizing them in a deeper architecture instead of in a shallow architecture gives you, okay, let you start with an advantage. And the advantage is this richer representations. In a following paper, we investigated this aspect more from a dynamical system theory perspective. And we derived mathematically how to compute the local Lyapunov exponents of deep reservoirs. So the outcomes can be found in this paper. And you can find, let's say, the numerical aspect represented in this plot in this figure. So, well, coming back to the mathematics, one important interesting thing is that you can take advantage of the fact that the Jacobians of the network in this case, as a lower triangular block structure, and this simplifies the analysis a lot. So I like this structure also that appear as a consequence of the kind of connections that you have in the topology. Well, numerically, like I said, we find that keeping the total number of recurrent units on par, a deep network, that is the blue line here in the plot, reaches a value of this maximum local Lyapunov exponent that is much closer to the edge of chaos. That is 0 here in the plot, in comparison to what can be achieved by shallow counterparts in orange and yellow in the figure. So it's more rich in this sense. And you can use this intrinsically richer, deeper dynamics given by the deep organization to have a very good performance in practical applications while keeping your training algorithms very simple, like a linear regression. And an example I would like to mention, just one among all the others, is an example in which acoustic networks are used to predict blast furnace of gas production, a particular type of byproduct gas that is obtained in industrial plants. So not only the predictions are very good overall, like you can see here in the image and in the table, but they're also very competitive and even better than much more complex architectures like long short-term memory networks or even gated recurrent units. So this is an observation that we did in several papers, that making the reservoir deep um, is a way that you can use to easily outperform gated architectures that are trained. Okay, so trainable gated recurrent units or long short-term memory. So have a look at our book chapter for further examples of this. And as you can guess, implementing deep reservoir computing algorithms is quite easy. So I think this is one of the major strengths of the approach. So to get an idea, you can have a look at my GitHub page for an implementation that uses TensorFlow and Keras. And you can see the code. I just sketched the code in the slide. You cannot actually read the code, but it's that code, trust me. And well, actually, you can see that the code is really just a page of code, and most of the lines are actually comments. So the code is very short, it's very simple to use. You can have a look and you can give a try if you want in your projects. Just have a look at the GitHub. Okay, and in the very last part of this tutorial, I would like to show you briefly what happens when we move from time series to more complicated forms of structured data like the graphs. So in these cases, your input doesn't come in a form of a static information like an image, for example, or like a temporal sequence. Instead, it comes in the form of a graph. For example, a graph that can represent a chemical compound, like in this slide, where the atoms are the vertices of the graph and the bonds um, are the edges between the vertices. So you want to give the structured input to your neural network, and you want the neural network to learn, for example, to classify these structures based on the fact that the molecule is toxic or safe for your health. And to extend the previous framework, also for this case, we consider the application of the same neural network architecture to every vertex in the input graph. So essentially, now we replace the concept of the time step with the concept of a vertex. And we replace the concept of the previous time step with the concept of the neighborhood for a vertex. Okay, so what we do is we compute a state or an embedding HV for every vertex in the input graph as a nonlinear function of the input features attached to the vertex. For example, in a molecule, this may encode, for example, the type of the element for that atom, and of the embeddings of the neighbors. So for each graph, we have a set of equations like this one. In this slide, this can be conveniently grouped together to form a single equation. Okay, so we have collected the embeddings in a matrix H here. So as you can see, this is a recurrence equation because H is both on the left-hand side and on the right-hand side. So a unique solution that is a unique embedding for the input graph does not exist all the time. So like, for example, this equation might not admit a unique solution when you have cyclic structures or undirected edges in your input graph. But fortunately, we can leverage all of our previous analysis and find a way to compute effective embeddings using reservoirs. In particular, we use the basic idea of treating this equation as the equation that drives a dynamical system. So in practice, we can encode the input graph as the fixed point of this dynamical system. So to have a fixed point, for example, we can impose a stability constraint to the iterated map of the dynamical system, just like in the case of conventional reservoir neural networks that we have seen before. So we call this graph embedding stability property, so graph embedding stability, GES property, which generalizes the echo state property described previously in the tutorial. So in practice, what you do, you have a large layer of graph reservoir that implements this function. And you can treat now this equation like a discrete time dynamical system here. So what you do is the following. You initialize randomly the layers weights under this GES property, graph embedding stability property. And then for every graph, you start with a 0 state as initial condition, and you iterate this equation until convergence to the fixed point that depends on the parameters of the equations that are x, the input features, and a tilde, that is the normalized adjacency matrix of the graph. So you can find more information also on the theoretical side on all these aspects in our paper from the last year, AAAI 2020. We call this the fast and deep graph neural network. Okay. So in practice, in this case, we use a deep and randomized construction of the neural network for graphs. And so in practice, we start from our first reservoir for graphs, where the dynamics depend on the input graph features. And we bring this layer to convergence to its fixed point H1 star. And then we use the information in this fixed point to drive the dynamics in the second layer. And then we bring also the second layer to its fixed point H2 star. Okay, so this way we continue until the end of the architecture, where the fixed point of the layer L-1 drives the dynamics of the last layer L. And we bring to convergence also the last layer. So we have this HL star. And now that we have all of our embeddings computed like the fixed point of our set of nested dynamical systems over graphs, we can use these to feed our readout tool where the learning takes place. And this happens like before solving a linear regression problem. So again, we have an internal representation function, the FR function in the previous slides, that is a deep composition of multiple randomized layers over the graph, and an external output function computed in the same usual way as described at the beginning of our journey in the tutorial. And in practice, this deep and randomized approach is very effective. For example, in graph classification, and compares very, very well to neural networks for graphs, kernel for graphs, hybrid models, like it is shown in the chemical domain in this slide, and also in the social network analysis domain. But not only it's accurate, it's also very fast. And for example, you can run these algorithms even in fractions of seconds. And even if you don't have GPUs, I think this is important, or any kind of hardware acceleration like it is shown in our paper. Great, it's now time to draw our conclusions. Okay, so in this tutorial, I try to guide you through a tour of randomization-based methodologies to build deep neural networks. So the tour was not exhaustive, I know, but I hope it was at least inspiring to a certain extent. Basically, we have seen how randomized neural networks, where most of the times the hidden layers connections are randomly drawn under certain conditions and then are left untrained. Well, this kind of neural networks can provide a great trade-off between accuracy and complexity. So at the very least, they can give you a very strong baseline in many problems. For me, they're also intriguing because they use as much as possible the architectural biases in deep neural networks to achieve a performance that is close to that one that can be achieved by fully trained models, yet at a fraction of the training times. And from this perspective, deep randomized neural networks are important from the mathematical analysis. So they are good tools for mathematical analysis to investigate these properties that are intrinsic to the deep architectures. And finally, we have seen how flexible and general this approach is. And in fact, it works very well in feed-forward models, like we've seen in the first part of the tutorial, in the recurrent models, like we've seen in the last part of the tutorial, for time series, and also for neural networks for graphs. In future works, for example, could investigate hybrid models. So this fully trainable and fully randomized networks, we have also said during the tutorial, are two extremes of a wide range of architecture. So there's a continuum of models that only today is starting to be explored. So I think this is a good direction to pursue. And for example, these deep randomized models can exploit adaptation, could exploit adaptation, perhaps in an unsupervised fashion. And I think they would be an ideal framework to test new algorithms, alternative to backpropagation and backpropagation through time. So not only they can use this algorithm, they can be a good test for those kind of algorithms. And finally, I believe that in a few years, in the immediate future, this is a push in this area of research can come from the synergy with implementations in neuromorphic hardware. So neuromorphic hardware, in particular in unconventional hardware, can be an important aspect of research for the future years. Great. Let me finally say that this tutorial is a part of the activities of a couple of recently established task forces, the task force on randomization-based neural networks and learning systems, and the task force on reservoir computing. So come have a look at our web pages if you are interested in the topics that I touched in this tutorial. Well, and that's enough for this tutorial. I remind you that the content is mostly taken from our recent book chapter called Deep Randomized Neural Networks. So I hope you enjoyed this journey, and I thank you for watching this video. Ciao, 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 ciao.